Here's lesson 2, solving quadratics by completing the square. Let's start this lesson by going through an investigation where we analyze this quadratic function that's in standard form, y equals x squared plus 6x plus 8. We'll start by finding its x-intercepts, or zeros, using the method of factoring, which we learned in last lesson. But then I also want to introduce you to the new method, finding the zeros of the quadratic by completing the square. And we'll do that by, in part C, converting the quadratic to vertex form by completing the square. And then in part D, then rearranging the equation to isolate x to find the zeros, or the x-intercepts. So by the end of this investigation, you'll have another method for finding the zeros of a quadratic equation. And that's important because not all quadratics are factorable. But we'll start off with this one here that is factorable. Let's start by finding its x-intercepts. And I remember any point that's on the x-axis has a y-coordinate of 0. So I'll start by setting this y value to 0. And then because this quadratic is in standard form and has an a value of 1, a b value of 6, and a c value of 8, I can solve for when this quadratic is equal to 0 if I can get it into factored form. And I can do that by finding two numbers who have a product of the c value, 8, and a sum of the b value, 6. The numbers that multiply to 8 and add to 6 are 2 and 4. 2 times 4 is 8. 2 plus 4 is 6, which means this quadratic can be factored to x plus 2 times x plus 4. And now that it's in factored form, it'll be easy to see when the product of these two factors is equal to 0. The product would be 0 if either of the factors were 0. And x plus 2 would be 0 if x was negative 2. And x plus 4 would be 0 if x was negative 4. So if x was either of those values, it would make this whole product be 0, which means those are the x-intercepts of the quadratic. And then in part B, it says use those x-intercepts to find the vertex. Well, because of the symmetrical properties of parabolas, I know the x-coordinate of the vertex is going to be right in the middle of the x-intercepts. So I'll find the x-coordinate of the vertex by finding the average of the x-intercepts. And I can find their average by adding them and then dividing by 2. That gives me negative 6 over 2, which is negative 3. So the x-coordinate of the vertex is negative 3. And then to find the y-coordinate, I can just take that answer of negative 3 and sub it back into the original equation for x. So I'll go ahead and do that. And then evaluating this, I have 9 minus 18 plus 8, which gives me a y-coordinate of negative 1. So the vertex is at the point negative 3, negative 1. And now that you remember how factoring can find both the x-intercepts and the vertex of a parabola, let me show you how the method of completing the square can find those same two pieces of information. Let's start by actually converting the quadratic into vertex form by completing the square. So let me rewrite the quadratic equation. And now let's turn this standard form quadratic into vertex form by completing the square. And if you're not aware of this method that gets a standard form quadratic into vertex form, go back and watch my lesson on completing the square so you can fully understand the whole process I'm about to show you quickly here. The main thing you need to know is to get the quadratic into vertex form, we need to create this binomial squared. We need to create a perfect square trinomial. So if I'm able to create either of these structures from the standard form equation, when I factor it, I'll get this binomial squared, which is the key component of vertex form. And as a reminder, how we can create that perfect square trinomial is we start by putting the first two terms in brackets. If there was something in front of the x squared other than a 1, we would have to common factor it out, but there isn't. So what I'll do next is inside the brackets, I'm going to add and subtract a number that is going to turn it into a perfect square trinomial. And to figure out what number we add and subtract, we take the coefficient of the x, which is 6. We take that 6, we cut it in half, and then we square the result. Half of 6 is 3, and when we square it, we get 9. So I'm going to add and subtract 9 in the brackets. So really what I did, I added 9 minus 9. So I added 0. So I haven't changed the value of the quadratic at all. But I don't actually want this minus 9 in the brackets. So I'm going to remove it from the brackets by putting it out with the plus 8, by multiplying it by whatever is in front of the brackets, which in this case is just a 1. I'm going to move this over a bit so I have some room. And all I have left to do is to factor this perfect square trinomial that I've created. I need to find numbers that have a product of 9 and a sum of 6. And notice the numbers that work are 3 and 3. It's the same number twice, which means we've done this properly. This quadratic would be able to factor to x plus 3 times another x plus 3. which we could just write as x plus 3 squared. And then negative 9 plus 8 is negative 1. And we can see from this vertex form that the vertex is in fact at negative 3, negative 1, which we got earlier in this investigation. But not only is vertex form good because the h and k values give us the vertex, but now that it's in vertex form, I could do part D, where it says solve for the x-intercepts by rearranging the vertex form equation to isolate x. So once again, if I want the x-intercepts, I know I can start by setting y equal to 0, and now I can just rearrange this to isolate x. And when rearranging an equation, I follow BEDMAS in reverse. Start with adding and subtracting. So I'll take this negative 1 to the other side by adding 1. And now I'll move this squared to the other side. The inverse of squaring is plus or minus square rooting. So plus or minus the square root of 1 is what x plus 3 would be equal to. And the square root of 1 is of course 1, so I just have plus or minus 1 equals x plus 3. And then I'll continue over here. Subtracting this 3 to the other side, I have negative 3 plus or minus 1 equals x. And now I can split it into my two possible answers. X being equal to negative 3 plus 1, and x also being equal to negative 3 minus 1. So my first answer for x is negative 2, and my second answer for x is negative 4. Notice those are the same two x values that we got when solving for the x-intercepts earlier in this investigation by factoring. And a key thing I want to point out to you here, make sure when moving a squared to the other side, the inverse of squaring, you always have to do plus or minus the square root. So what we've discovered here is a quadratic equation in standard form can be solved for x by first converting to vertex form by completing the square, and then rearranging to isolate for x. And if a quadratic has solutions, this method will always work, unlike factoring, which only works when a quadratic has rational solutions. But let's go ahead and go through a few parts of this where we're going to solve quadratics that have rational solutions and irrational solutions and no real solutions, all by completing the square. Of those sections, the only section that we could also do by factoring would be this section right here where the quadratic has rational solutions. Let me take you through that. Notice in this first example, example 2a, we have a standard form quadratic set equal to 0. And we're going to solve it by, the question says, completing the square. To solve it by completing the square, I have to get it into vertex form. And to do that, I'll put the first two terms in brackets. Nothing other than a 1 in front of the x squared, so I don't have to common factor anything out. But I do have to add and subtract in the brackets a value that will turn this quadratic into a perfect square trinomial. To find that number, I'll take the coefficient of the x, negative 12, I'll cut it in half, and then square the result. Half of negative 12 is negative 6, square it, I get 36. So I need to add and subtract 36 in the brackets. But I don't want the minus 36 in the brackets, so I'm going to move it out front by multiplying it by the 1 that's in front of the brackets. And then to get this into vertex form, the last thing I have to do is factor this quadratic, which should factor to a binomial squared. Let's check. What are the numbers that multiply to 36 and add to negative 12? The numbers that work are negative 6 and negative 6. Good, it's the same number twice, which means that quadratic would factor to x minus 6 times another x minus 6, which we'll just write as x minus 6 squared. And then collecting my constants together, negative 36 plus 20 is negative 16. Now that it's in vertex form, I can just try and isolate the x in my equation. I'll add 16 to the other side, and then I'll get rid of this squared by plus or minus square rooting, and then I'll move this negative 6 by adding 6 to the other side. So I have 6 plus or minus root 16, and root 16 is just 4. So I have 6 plus or minus 4. And then let me shrink this a bit so I have room to write my answers. My final answers, I can split it into both possible answers. My first answer is 6 plus 4, which is 10. And my second answer is 6 minus 4, which is 2. So two possible answers for x. We could check both of those answers in the original equation. Subbing in either 10 or 2 for these x's should make the left and right side of the equations equal. And now let's do part B, where we'll get rational answers as well. Notice part B, the quadratic isn't set equal to 0 yet, it's set equal to 10. And to do the method of solving by completing the square, we need to start by setting the quadratic equal to 0. So I'll move the 10 to the other side, giving me 0 equals 2x squared minus x minus 10. And then to solve by completing the square, I have to get this into vertex form. So the first two terms go in brackets, and then whatever's in front of the x squared, if it's not a 1, it has to be common factored out. So I'll put a 2 out front, and then I'll divide both the terms in the brackets by 2, giving me x squared minus a half of x. And then remember, inside the brackets here, I actually want to turn this into a perfect squared trinomial. So I'm going to have to add and subtract half of this value squared. That would be equal to negative a quarter squared, which is 1 over 16. So I have to add and subtract 1 over 16. But I don't want this negative 1 over 16, so I'll take it out by multiplying it by the 2 that's out front, making it a negative 2 over 16, which reduces to negative 1 over 8. And now I have to factor this quadratic. I need to find numbers that have a product of 1 over 16 and a sum of negative 1 over 2. And remember, if we've done this properly, it's going to be the same number twice that satisfies this product and sum, and that number is always going to be half of the coefficient of the x. Half of negative a half is negative a quarter. And watch, negative a quarter times negative a quarter is 1 over 16, and negative a quarter plus negative a quarter is negative 2 quarters, which is negative a half, which means I could factor this quadratic to x minus a quarter times another x minus a quarter, which I'll just write as x minus a quarter squared. And then when collecting my constants, I'm going to need to get a common denominator. Right now it's negative 10 over 1. Multiplying top and bottom of that by 8, I get 80 over 8 is equal to 10. So negative 1 over 8 minus 80 over 8 is negative 81 over 8. And now I can just rearrange this to isolate for x. I'll start by moving the constant term to the other side. And next, I'll divide the 2 to the other side. It'll go in the denominator with the 8, making it 81 over 16. And then I can move the squared by plus or minus square rooting the other side. And then let me make a bit of room here so I can finish the question. I'll take this negative a quarter, add it to the other side. So I have a quarter plus or minus 81 and 16 are both perfect square values. So when I square root it, I get 9 over 4. So I have two possible answers for x. A quarter plus 9 quarters and a quarter minus 9 quarters. So my first answer, 1 over 4 plus 9 over 4 is 10 over 4. Dividing top and bottom of that by 2, I see that's equal to 5 over 2. And my second answer, 1 over 4 minus 9 over 4 is negative 8 over 4. And negative 8 divided by 4 is just negative 2. So there's my second answer for x. And both of those answers for x, those are the solutions to the original equation, and you could check them. If I subbed either of them in for the x's in the original equation, it should make the left side of the equation equal to the right side of the equation. And before we move on, I want to make sure you understand why we're putting this plus or minus square root when we move a squared to the other side. Why do we need this plus or the minus of the square root? Well, have a look at these answers, 10 and 2. Those are the answers to the equation, so they should satisfy the equation at any step in our process, including this step right here. If I take this 10 and sub it in for this x, I would have 10 minus 6 squared, which is 4 squared, which is 16. But 4 is not the only number that when you square it, you get 16. Like, watch what happens when we sub 2 in for this x. I would have 2 minus 6 squared, which is negative 4 squared, and negative 4 times negative 4 is also 16. So because when we square both 4 and negative 4, we get 16, we need to make sure we get both of those answers, which is indicated here with the plus or minus 4. Those are the two values that when you square them, you get 16. And now let's move on to the next section. But actually, we have a blank to fill out here. It says, notice for each of the equations in this question, there were rational solutions. And remember, a rational number is a number that can be expressed as a fraction. So 10, 2, 5 over 2, and negative 2 are all rational, which means both of the original equations could have been solved by factoring, which is what we did in lesson 1. Hopefully you noticed in lesson 1, all of the quadratic equations we solved had rational solutions. But what happens if a quadratic doesn't have rational solutions? Let's look at part 3 of this lesson where these quadratics have irrational solutions. If I tried to solve these quadratics by factoring, I wouldn't be able to find any numbers that have a product of negative 21 and a sum of 6. So because those numbers don't exist, Solving by factoring doesn't work. And in fact, the only way we can solve this quadratic is by using the method of completing the square. So not only does completing the square work when there are rational solutions, but it also works when there's irrational solutions. Let me prove that to you. Notice the standard form quadratic is set equal to 0 already, which is perfect. So now I want to get the quadratic into vertex form by first putting the first two terms in brackets, and then whatever number is the coefficient of the x squared, in this case -3, that has to be common factored out from the first two terms. So I'll divide out a -3, and when I divide those first two terms by -3, I get x squared minus 2x. And then I want to turn this quadratic into a perfect square trinomial, and I can do that by adding and subtracting half of this number squared. Half of -2 is -1, and when I square it, I get 1. But I don't want the -1. I can get it outside the brackets by multiplying by the -3 that's in front. And then factoring this quadratic, the numbers that have a product of 1 and a sum of -2 are -1 and -1, which means that quadratic would factor to x minus 1 times another x minus 1, which I'll write as x minus 1 squared. And now I'll just rearrange the equation to isolate the x. I'll start by moving the 10 to the other side, and then I'll divide this -3 to the other side. A negative divided by a negative is positive, and then I'll move this squared to the other side by plus or minus square rooting. And then I'll move the -1 to the other side by adding it, giving me my two possible answers. My first one would be 1 plus the square root of 10 over 3, and my second answer is 1 minus the square root of 10 over 3. Now this is the first time the number underneath the square root hasn't been a perfect squared value, which means the values of these two are irrational. So there's nothing else we can do to simplify these answers if we want to leave them in exact form. So these are the exact answers to the original equation. But if we were interested in the approximate answers, so the approximate decimal value, we could type these on our calculator and get those values. Typing 1 plus the square root of 10 thirds, I could get the approximate x value of 2.83, and 1 minus the square root of 10 thirds is -0.83. Now notice I used the approximately equal symbol because these are just approximations. The square root of 10 thirds is irrational, meaning it has a decimal value that goes on forever with no repeats or patterns. It can't be expressed as a fraction. So if a question asks you for the exact answer to a quadratic, you'll leave it in this format. But if it asks you for an approximate value, you can use a calculator to get the approximate value and round it to how many ever decimal places are indicated. Now let's try one more. This one we have another standard form quadratic set to 0. You might first want to try and solve it by factoring. So you would try and find numbers that have a product of -8 and a sum of -6. But in fact, those numbers don't exist. So that means there are not going to be any rational solutions to this equation, but there may be irrational solutions. And to find those, we can try the method of solving by completing the square. We'll get the quadratic into vertex form by putting the first two terms in brackets. It's just a 1 in front of the x squared, so I can skip to the next step, where I create a perfect square trinomial by adding and subtracting half of -6 squared. Half of -6 is -3, and when I square that, I get 9. And then I'll take the -9 out of the brackets by multiplying by the 1 that's in front, and then factoring this quadratic in the brackets, I just have to find numbers that multiply to 9 and add to -6. And the numbers that work are -3 and -3, which means it factors to x minus 3 squared. And now I can just isolate the x. I'll move the -17 to the other side, and then to get rid of the squared, the inverse of squaring is plus or minus square rooting. And the square root of 17 is an irrational value, just like I thought we would get. So the last thing to do to get the exact answers is just move the -3 to the other side. So I have two possible answers. My first one would be 3 plus root 17, and my second possible answer, 3 minus root 17. Those would be my exact answers, but using a calculator, I could get the approximate answers of 7.12 and -1.12. So in this section, notice that all of our answers were irrational. That means that neither of these quadratic equations could have been solved by factoring. That's why this solving by completing the square is such a useful strategy. And then let's look at the very last scenario. What if a quadratic doesn't even have any real solutions? So let's have a look at this quadratic here. When solving when a standard form quadratic is equal to 0, You'd probably start by trying to factor it, finding numbers that multiply to 10 and add to -6. But those numbers don't exist. So that would tell you that if there are solutions, they're irrational, and you would have to do solving by completing the square. So let's go ahead and try and find those irrational solutions if they exist. To put it into vertex form, we put the first two terms in brackets, and then I'll create my perfect squared trinomial by adding and subtracting. Half of this -6 squared, half of -6 is -3, square it to get 9. I'll take the -9 out of the brackets, and then I'll factor this quadratic. It's the same one we had for the last question, where we want a product of 9 and a sum of -6. The numbers that work are -3 and -3, so it would factor to x minus 3 squared. And now watch what happens. When isolating the x, I'll start by subtracting 1 to the other side, and then when I move the squared to the other side, I would plus or minus the square root of -1. And what's the square root of -1? That means what number squared equals -1, right? And that's what this equation says right here. We're looking for what can I square and get -1. Well, when you square a value, it becomes positive, right? Anything multiplied by itself is positive. Well, that's true in the real number system. So that actually means there are no real solutions to this equation now. I could finish isolating the x and say I have x equals 3 plus or minus the square root of -1. But because underneath the square root is negative, that's not a real number. And in fact, there's a symbol for that. The square root of -1, we can write that as I. I meaning imaginary. The square root of -1 is an imaginary number. Now in this course, you're not expected to express an answer like this. Once at this step, seeing that we're square rooting a negative, you can actually stop the question there and just say there are no real solutions. So anytime when solving a quadratic by completing the square, if you have the square root of a negative value, there are no real solutions to that quadratic. So notice not all quadratics have real solutions. This quadratic only had what we call our imaginary solutions. And now let's finish off the lesson by doing an application question. It says for this quadratic that's in standard form, find the vertex, the x-intercepts, and then sketch a graph. Now to find the vertex and the x-intercepts, we have two options. We could complete the square, or we could factor it. Since we've been completing the square for the whole video, why don't we do this one by factoring? So let's take this quadratic and let's find its x-intercepts by factoring. To find the x-intercepts, I'll start by setting it to 0. And now to factor it, I would need to find two numbers who have a product of a times c, so a product of 2 times 3, which is 6, and a sum of the b value, -5. The numbers that work are -2 and -3. So I have to split the middle term into -2x minus 3x. And then I factor by grouping. From the first two terms, I take out a 2x, and from the last two terms, I take out a -3. And I have the common binomial of x minus 1. When I take out that common binomial, I have 2x minus 3. Now that it's in factored form, the product would be 0 if either of the factors were 0. X minus 1 would be 0 if x was 1. And 2x minus 3 would be 0 if x was 3 over 2. And 3 divided by 2 is 1.5. So I have x-intercepts at both 1 and 1.5. So I can plot those. And I know the vertex is going to be in the middle of those two. So the x-coordinate of the vertex is going to be at the average of 1 and 1.5. And to find their average, I can just add them and divide by 2, which gives me 1.25 as the x-coordinate of the vertex. But I don't know the y-coordinate of the vertex yet, but I do know its x-coordinate is 1.25. So let's find its y-coordinate by subbing 1.25 into the original equation for x. And if I do that, I get -0.125. So my vertex is at 1.25, -0.125. So I can plot that point. And then for accuracy's sake, let me plot a couple more points. Seeing the quadratic in standard form, I know the constant value 3 is going to be the y-intercept. So I can plot the y-intercept at 3. And then if the y value is 3, 1, 2, 3, 4, 5 units to the left, if I move 5 units to the right, the y-coordinate should be at the same height. And now connecting these points with a parabola shape, I have the graph of that parabola. So hopefully you made it to the end of this lesson and you feel comfortable solving quadratics by completing the square. And if you stay tuned for the next lesson, you'll see how this method leads to a really important formula when dealing with quadratics. It's the quadratic formula, which is going to be a great tool for solving quadratics that have rational, irrational, or non-real solutions without having to go through this process of completing the square every time. Jensen Math!